We are going to be talking about gravity loads for structures up to 3 stories using the 2015 WFCM engineering provisions. So hopefully you've seen the description and learning objectives, so I won't spend a lot of time there with that. But we will provide some background and calculations similar to what we did last month for lateral loads. And so today we'll be talking about gravity loads from ASCE 7-10, and that includes snow, live, and dead loads for various building components and systems, and see how those work down through the structure, and talk about load path as we work through. So let me keep going here to the first poll question, and we'll get a sense of who's with us today in the audience. Marcy?
All right, some of you got a preview of this earlier when we were testing, but if you could go ahead and vote for us now again, I would appreciate it, just so we can kind of see who's with us. We'd like to welcome you all. So, and as always with our polls, I'll give you about 30 to 45 seconds, and then wait for about 80 to 85% of you to vote. So. All right, I'm going to go ahead and close the poll since I've got about 80% of you. And then sharing it. We've got 70% engineers, 19% code officials, 7% architects, and 3% others. So welcome to you all.
Okay, yes, welcome. We are glad you're here, and as we work through the program today, we hope to give some insight and information that will be helpful for all of you. One of the first things we look at when we talk about the wood frame construction manual is whether or not you can even open the book. So this table 1, right inside the front of the, after the table of contents, one of the first things you'll see are the applicability limits for the wood frame construction manual. Let me just zoom in here a little bit more, because as I mentioned, we've talked about lateral loads in previous webinars. Last month we looked at the wind load provision, so we won't spend any time this week looking at lateral loads. That one is recorded and available on our website. I think Brian will throw a link up there if you are interested and didn't make it last month and would like to learn more about the background for wind load provisions used in this document. Then you can go and actually earn a 2-hour CEU with that one online, and that's free as well. So for any structure that we want to use or design using the wood frame construction manual, the mean roof height has to be, has to be 33 feet or less, and number of stories 3 or less, and the building length and width 80 feet or less. Now, it doesn't mean you couldn't design a larger structure, a structure larger than 80 feet in length. It just means you'd have to break it up into multiple structures to accomplish that. So if you had a strip shopping center, for example, and say it's an 80 by, or say 40 feet deep and 160 feet long, you could build or design 2 80-foot structures in that strip shopping center. We've talked about the applicability of the wood frame construction manual in the past, so if you're wondering why I'm talking about strip shopping centers, that's in accordance with Section 2309 of the International Building Code, the new International Building Code 2015 edition. Does have application for this beyond 1 and 2 family dwellings. But we get down to the gravity loads then, and here are some of the assumptions that are outlined for partition Dead loads were at about 0 to 8 pounds per square foot of floor area. Wall assembly dead loads 11 to 18 pounds per square foot. And you might ask, well, why that range? Some of it has to do with being a little more conservative with seismic design, so those loads will be a little bit higher for seismic and a little bit lower for wind, just because of the way those loading assumptions are for various purposes. Floor dead loads are pretty standard, 10 to 20 pounds per square foot. Roof ceiling assembly dead loads go all the way up to 25 pounds per square foot, depending on the what might be on the roof. Clay tiles and things like that could add up to some larger dead loads. The floor live loads of 30 to 40 pounds per square foot are really what limit us from having really broad application of this in multi-story commercial applications. So that's why when we talk about the application of the wood frame construction manual, we're usually for non-res applications going to be limited to one story or slab on grade, or the upper story of a pedestal type building. If you have a single wood frame story over top of a concrete pedestal that you might see in some planned developments. Those are all applications where this could be used beyond just residential applications. And so we can help you with that if you have questions about its applicability, but this floor live load is really where that keeps us from using it in multi-story commercial, where you might have 50, 60, 100 pound per square foot floor live loads, and we just haven't accommodated those in the document. So then ground snow loads go from 0 to 70 pounds per square foot, and we'll talk about that. We'll talk about balanced and unbalanced snow loads as we work through the presentation today as well. So I'm going to jump into a page here, and I apologize, this one did not make your handout, so don't go scrambling, think you've got the wrong handout. We just missed dropping this page in there. But up front in Chapter 1, if you have your wood frame construction manual, you can certainly see this. I'll show you, just take a look up here at 1.2.1.5, the different materials and products that this applies to. Prefabricated wood trusses are covered in this document, as is solid sawn lumber, glued laminated timber, and prefabricated wood I-joists, as is structural composite lumber. So there are provisions in the way we set up the tables in the wood frame construction manual allow the use of all of these traditional and engineered wood products. And so we'll show you as we go through the tables a little bit how we accommodate those. But I wanted us to sort of get that in up front so you know just the types of materials that can be used. We're not limiting this just to solid sawn lumber applications. Then we get into Chapter 2, which is our engineered chapter, and I'll talk again a little bit about the engineered versus the prescriptive chapter of the wood frame construction manual. We're looking strictly at Chapter 2 today, which has the engineered provisions. Primarily those are loads that we've calculated per ASCE 710 and are pretty going to be pretty standard today as we look at gravity loads. When we get into Chapter 3, then we've got a prescriptive solution to those loads that we calculate in Chapter 2. So what Chapter 2 allows an engineer, designer, or a code official that's doing plan check to do is see the background, see the load combinations, see how we've interpreted or used ASCE 7-10 for these low-rise structures, so that you have a good sense that this is not just a black box and that you can have some confidence in the tables and the values that come from those tables. So again, we cover lumber, I-joists, trusses, and allow for that. I mentioned this last month, but I'll mention it again, that joist spans for floors and rafters are going to be limited to 26 feet, not because we can't span further than that with trusses or I-joists, but because we've got load path issues to deal with. One of those load path issues is if a floor joist system at 16 inches on center lands, let's say it's a truss or an I-joist system. So we've got a truss or an I-joist system at 24 inches on center, and we've got studs in a stud wall, a bearing wall under that, spaced at 16 inches on center. Well, you're invariably going to end up with a case where that floor truss or I-joist ends up right in the middle of those two studs on double top plate. So we looked at the bending capacity of a double top plate with that concentrated load and determined that that's a reasonable limit for this wood frame construction manual. And so that's why you see those limits, and if you want to span further than that, then we need to look at interior load-bearing walls for I-joists or trusses and make sure again that we've got load path through the structure, or that we're lining up the floor joists and rafters with the studs below so that we don't overload the top plates that are in those bearing walls. Another nuance down here is we look at the wall systems and we look at the difference between Chapter 2 and Chapter 3. I've highlighted here that load-bearing wall height in Chapter 2 can be 20 feet. In Chapter 3, in the prescriptive limits, we're limited to a load-bearing wall height of 10 feet, and that's because the IRC has that limit for residential construction, conventional construction, and we've not tabulated in Chapter 3 to go beyond that 10-foot limit. So for load-bearing walls in Chapter 2, however, as a design professional, knowing what how these loads work and how to use them, you could design a tall wall, for example, in a foyer of a two-story structure, two-story house with a open foyer type look under a bearing wall. And so we'll look at some of the tables in a little bit that give you a sense of how that works. We've also got setback and cantilever limits, and we'll look at that as we go through a couple of these pages in the wood frame construction manual as well. So that's the table that kind of gives you a sense of what the limits on the engineered provisions are. As I mentioned, there's a separate table in Chapter 3 that have similar limits for using the prescriptive approach, but some of those limits are a little more restrictive. So we get into Chapter 2, and this is shows page 18 in the top left of your handout, page 18 of the wood frame construction manual. And what we've done here is just highlighted again some of the provisions that we're going to be looking at today, and what this gives you is a sense of the enabling provisions of the standard. For example, when we're going to calculate these thrust connections per section 2.2.6.7, connections to transfer thrust loads in the lower third of the attic space shall be in accordance with the thrust load specified in table 2.3. So this, again, a lot of times we do these seminars and webinars, we jump right to the tables. The enabling language is here and it's outlined in such a way that covers the entire load path of the structure. So this is one of the tables we'll look at today. When we get into floor systems, we'll do some things that are pretty straightforward, like a floor joist application where we can look at single and continuous span floor joists in accordance with the property requirements of Table 2.7a and b. And so we're going to tabulate those for single span applications. Then we'll show how you can adjust those for continuous span applications. Also pretty straightforward are bearing load calculations in Table 2.7c. But I also want you to notice while we're here, this section 2.3111 for notching and boring, and these are provisions that are probably familiar to you from the NDS or other building codes that limit notches and holes in joists, and so those would apply and are applicable here as well. So we try to make it sort of a comprehensive document by including things like that. Next, talk just briefly about end restraint. And again, we covered lateral loads last week, but as we're framing this up and you see things like restraint against twisting at the end of each joist, and that fasteners be capable of resisting a 300 inch-pound twisting moment. We've got shear walls that are taking shear on top of these floor systems, and so we got to make sure we've got blocking or fasteners in place to accommodate those types of things. We've got the lateral stability requirements here in 2314, comparable to what you see again in documents like the NDS. So depending on the nominal depth to breadth ratio, 2:4 for example, as a depth to breadth ratio of 2, says no lateral support required at the ends. Let's see if I missed anything at the top of the second column. Nope, we're good there. I did mention that, let's see, we do talk a little bit about single and continuous floors supporting load-bearing walls. So if we have load-bearing walls perpendicular to the joists, we don't want to offset those from the girders or beams. So if we've got those types of setbacks or cantilevers here shown in this next section, then we've got limits for that and diagrams that show those limits. Again, we're trying to maintain load path, but again, as an engineer, if you would like to design those cantilevered conditions with additional floor loads and gravity loads of that exterior load-bearing wall, then we're going to look at a table 2.11 here a little bit that give you those loads. And so you could, using provisions of Chapter 2 and those load tables, design in those additional loads on your floor systems. So again, the tables have a lot of application. If you look carefully here at the enabling language in Chapter 2, you'll see where you can use those tabulated values. Then on to page 20, and it's 20 that's shown or printed in the document. Page a different page number for the PDF, but so floor openings, we talk about making sure that if you have floor openings that you're designing your fasteners, connections, and stiffeners around those openings. If it's less than 2 feet from an exterior wall, then we're going to need to frame that wall, that exterior wall, using full height studs or a beam to resist the gravity, lateral, and uplift loads at that location due to that discontinuity in the floor diaphragm. So again, load path, and since this is the engineered section of the code, we may not provide a solution to these provisions, but pointing it out for the design professional to make sure that we handle the load path. Then again, what I-joist systems are contemplated here in the standard, and we say pretty clearly here, and what's highlighted on the screen here is that the I-joist floor systems are in accordance with this section, the Governing Building Code, and any additional requirements set forth in the manufacturer's code evaluation report, but that we can use single and continuous span I-joists based on the capacity requirements in tables 2.8a and b. And so we'll show you those capacity tables, which then would allow you, once you have an M, V, and EI value from those tables, to go to the manufacturer's literature and specify those products. Notching and boring according to the manufacturer's requirements, bearing conditions, and bearing capacity. We'll be able to show those capacities, but those would also come from the manufacturers. They'll have their own end restraint requirements, bridging, other things that are very specific to I-joists, setbacks and cantilevers. Again, a lot of that is based on the requirements of the manufacturer, but we, again, try and be as comprehensive as we can here, showing you what to look for and address to maintain load path. Floor trusses also contemplated in the document, and so we know that there are standards for that developed by the Truss Plate Institute, ANSI TPI-1, for floor truss design. Any notching and boring there has to be per the approval of the truss designer, and then bearing requirements are going to be similar to other bearing requirements. The end restraint in this case is likely going to be covered by a document developed by the Structural Building Components Association and TPI, their building component safety information sheets for handling, installing, restraining, and bracing trusses. Also similar for cord and web bracing. So again, you see as comprehensively as possible provisions for different types of products. Then we get into wall systems, and for the exterior walls, we're making sure that we point to table 2.9b or table 2.11 for the gravity loads that are specified in those particular tables, and we'll be taking a look at those in a little bit. So I'm going to stop there, and we had a little bit of a glitch with the poll question that came with your handout if you downloaded that handout. So take a look at the revised question here, and I'll bring Marcy back to take care of our next poll, but it'll be showing up correctly on the poll that you get to vote in.
All right, here we go. So the WFCM includes provisions for solid sawn lumber, glulam, wood I-joists, structural composite lumber, or all of the above. All right. Got about 70% of you, so about 10% more, excuse me. I don't know, maybe this one was a little too easy. I've gotten,
you think?
Yeah.
Yeah, well, maybe we'll try and get a little tougher as we go.
Okay, so, all right, I've got 78%, so I'm going to call that good.
All right.
And the answer here, we've got 94% say all of the above, and just a smattering for the others. So I'm hoping that all of the above was the answer.
Yes, that is correct. All of the above is the correct answer. And the reason we just tweaked the question here on the screen a little bit is we obviously don't provide design provisions, specific design provisions for engineered wood products like I-joists and trusses and structural composite lumber. But we do include provisions for all of those to accommodate those in the standard. And so that's what we wanted to make sure that it's clear. It's often misperception, I guess, that this document only applies to solid sawn. And so we want to make sure folks understand that we accommodate engineered wood products as well. So we'll keep moving here then through the document. And so I mentioned this a little bit earlier, the wall systems, and pointing to table 2.9b and 2.11 for wall systems, and so we'll take a look at that here in a little bit. Let me go down here and talk a little bit about top plates and bottom plates, then we'll jump back up to the top of the page here. But in 2.4.1.2, top plates, exterior stud walls shall be capped with a single or double top plate with bearing capacity in accordance with 2.9b and bending capacity in accordance with table 211. And so we will have some gravity load tables in a little bit to allow you to design not only the studs but the top and bottom plates. Headers, 24141 starts there at the bottom of the page. Now we'll jump back up here to the top, and need to be in accordance with the capacity requirements of table 211. So table 211 is a really sort of utilitarian table for the gravity loads for wall systems, for studs, headers, top and bottom plates. So it really gives you a good tool to use for all of those. Then we get into interior load-bearing partitions, also referencing table 2.9c and table 211. Again, the notching and boring provisions also apply to these exterior and interior studs. Not sure that those are necessarily covered as clearly in the codes or in the NDS. So if you are looking for notching and boring provisions for studs, they do show up here in the wood frame construction manual. So just make a mental note of that. We won't take time to work through all that here. But for the interior walls as well, top plates and bottom plates would need to be designed for those gravity loads, and any headers in those interior walls would also need to be designed. So that gets us through the wall systems. Again, trying to point out load path provisions for gravity loads as we work through here. Rafters in accordance with the maximum spans, and make a note here that the rafter spans are based on the horizontal projection of the rafter. So it's not the actual span of the rafter, but the horizontal projection. And we'll talk about that and those assumptions, and look at the commentary for some background on that. If you decide to design a ridge beam, which may or may not happen in a lot of residential structures, we do have a ridge beam table, and that's table 216 that shows how the loads for a ridge beam would be calculated. Obviously, there's an exception here that's carried through into Chapter 3 where a ridge board is permitted if the roof slope equals or exceeds 3 and 12, and then there's some provisions for that. But if we do that, then we got to make sure if we're using a ridge board that and that's in this highlighted area here at the bottom of the exception, the ceiling joist and rafter ties resist the thrust loads that are now present because we don't have a ridge beam. And so table 2.3 is going to give us those thrust loads, and then there's some additional adjustment factors because if we have a rafter tie, which can be raised up above the top plate, that's going to put some additional moment on the rafters, and we'll have to accommodate those rafter spans, the additional moment in those rafter spans with some adjustment factors. We're going to look at a hip and valley beam table, 2515, table 217. We've got a ceiling joist table, and so that's going to be pretty straightforward. We won't have to spend a lot of time on that. But again, we accommodate I-joists and do that with the capacity tables for rafters. I-joists, however, according to 2525 down here in the bottom right of this page on your screen, shall be supported on bearing walls, headers, or ridge beams. So here there's no option for a ridge board like we have for solid sawn. But hip and valley beams could be designed using I-joists, and we'll give the MV and EI capacities for those as well. So this then serves, the list of tables on page 61 of the wood frame construction manual serves as an outline for what we'll cover today in the remainder of the presentation. Now that you have the enabling language and we've talked through that, these are the tables that we'll be looking at. Once we've done a capacity table for a floor joist, however, we probably won't repeat that for a ceiling joist and a rafter, so we will move quickly through some of these to make sure that we are able to cover everything that we want to cover today. So that gives you a sense of what's in the remaining part of the seminar. So jump into page 66 of your handout, table 2.3, which is thrust connection loads. We alluded to that just a little earlier. If we have even a ceiling joist, it doesn't have to be a rafter tie, but if we have a ceiling joist, and let's jump down here and look at the picture, and if we're doing this at a live seminar, a lot of times I'll ask for somebody to tell me, what's the difference between a rafter tie and a collar tie, or a ceiling joist and a collar tie. What loads are we resisting there? And I want to make sure that we have an understanding of that. So I'm jumping down here to the picture. This shows the loads on a rafter tie or a ceiling joist. The ceiling joist, if you can see my arrow there, could be down on the top plate, and so we have a ridge board application, and we've got snow loads on that roof. It's going to be pushing the walls out where that top plate connection is. So the ceiling joist and the rafter ties or rafter ties are there to resist that outward thrust. So the table above is a calculation of those thrust loads. So this is different from a collar tie. A collar tie is connecting the top ends of the rafter together to resist uplift and to keep the ridge from opening up due to uplift loads. And so the collar tie table is one that we talked about last month in our webinar based on wind loads. A collar tie is not used to resist any gravity loads. It's in the upper third of the roof system and is used to resist uplift loads. The rafter tie or ceiling joist is what's used to resist thrust loads. And so that's what's tabulated here based on an assumed roof assembly dead load of 10 pounds per square foot. Come down here and assume a 30 pound per square foot ground snow load, a roof span of 36 feet, and a 4 and 12 roof pitch. We see that the thrust connection load highlighted there on your handout is 894 pounds per linear foot. So we're going to look in a second at the commentary to see how we calculated that value. But footnote 1 kind of summarizes what we just talked about. If we have a ridge beam, then those thrust connections are not required because we've supported the top edge of the rafter, the top end of the rafter, and we don't get those loads pushing out at the bottom, at the top of the wall. Let's jump to footnote 3. That has to do with we tabulate per linear foot. So if you had rafters, for example, spaced at 16 inches on center, then you'd adjust that value up by 1/3 to get the true load on that particular rafter. Also, if you have a ceiling joist lap splice, let's say you can't span that entire 36 foot with solid sawn 2x6 or something like that, so you got to splice it in the middle, then you'd have to make sure your connections handle that load as well, where you're splicing together. Then this equation here that's highlighted is what we do to calculate our rafter tie load. So once we come up above the top plate, now we've increased the loads on that rafter tie just based on simple statics. And so these factors can be calculated, and we've got an equation here, T required equals T tabulated, and it's based on the height of the top plate to roof ridge height and the ceiling height in the attic space measured from the top plate, H sub C. And if you have your wood frame construction manual, you turn to Chapter 3. We tabulate those adjustments in Chapter 3. Here we just give you the equation, but if we're up 1/3 of the distance into that attic space, that gives us a factor of 1.5. So we would increase those thrust loads by 50% because we've raised that ceiling joist up into the attic space. Now, we can go as high as 1/2 up into the attic space, but take a look at this note here. Lateral deflection of the rafter may exceed 3/4 of an inch if you're located above 1/3. So that's going to take some additional consideration there if you do that. So once you get above 1/3, take a look at your lateral deflection of the rafters, because that can be pretty substantial. We're putting some pretty substantial loads and moments on the rafter at that point. So how do we calculate that? Well, it's pretty straightforward. Again, so the commentary to the wood frame construction manual is a separate document. We've sort of pulled those pages all together here in this handout for you. But if you're looking through your wood frame construction manual wondering where this page is, this is from the commentary. Separate document, second document that comes in the package. And for each of the tables in the wood frame construction manual, there is a corresponding table in the commentary. So this one gives the background for calculating thrust connection loads. They're tie forces that develop at the heel joint between the rafter and the ceiling joist. So that's typically a single shear connection. That can create some eccentric loads, and so you need to account for that if you have very high, substantially high loads. And also the overhangs are ignored because those are going to reduce the amount of thrust. So the value we highlighted in the table above is what we're going to solve for here. And we're going to use ASCE 710 as we talked about. And we're going to convert ground snow load to roof snow load using the provisions of ASCE 710. And so taking a 30 pound per square foot ground snow load, converting that to a roof snow load gives us 23.1 pounds per square foot, adding the dead load into that. So then we're going to take that maximum load and compare it to the unbalanced snow load, and so we've done that for you as well. But the maximum load for this particular application is going to be based on a balanced snow load, not an unbalanced snow load. So we've done those checks. You can do them on your own to satisfy yourself, but we've done that already, and we'll show you some more examples of that later on in the program. So then we're going to just some moments and solve for the tension heel joint force T and come up with that capacity, 894 pounds per linear foot, which is what we calculated earlier in the table. Again, the footnotes, if you've got 16-inch on center spacing, would require you to increase that, and you can see that increases to almost 1,200 pounds at 16 inches on center. Then that footnote 5 that we looked at earlier gives us the this gives us the background for increasing the loads as a function of that rafter tie being raised up above the top plate, and that's just quantified using a ratio of moment arms. And so again, we've gone through that background calculation for you, but this shows you how that all works. And again, those specific values are tabulated for you in Chapter 3. So diagram here showing you where we're summing moments about that right heel joint and coming up with the capacities. So let's jump on over to floor joist applications. Table 2.7a. Now we're on page 74 of your handout in the upper left. So we're going to look at a floor joist application with a 30 pound per square foot live load, a 10 pound per square foot dead load there, an L over D ratio of 360, and we're going to size a 2x10, and we're going to space those floor joists at 16 inches on center. So we come on down here to 16 inches on center, and the way we're going to approach this is we're going to tabulate a pretty standard E value. There are pretty standard E values here in this first column. 1.6 million PSI is what's shown. Then we're going to calculate a required bending capacity from that and a required span. So this then is the span that satisfies this E value and this bending value. So that 18-foot span is satisfied by this E value and this bending value. All right, so we're calculating based on live load deflection only, so take a look at your footnotes. Again, we've limited spans to 26 feet, and even once you get above 20 feet for solid sawn, you're going to have to check for availability above 20 feet. But for I-joists and other products, should be not an issue. So now we're in the commentary to this table. So wood frame construction manual commentary to tables 2, 7, A and B. We're going to calculate for this 30 pound per square foot live load. So here's under the background. Again, these are applicable for simple spans and continuous spans, and we'll look at some factors for you in a second for that. But the procedures first, you need to know your dead loads, joist spacing, joist size that you're going to attempt to solve for. Then you're going to select a modulus of elasticity, or E value, for that desired span. So as you can see, we won't be limited to just the 4 major species groups. That's the other thing that's useful for these tables. If you don't have Doug fir, hem fir, SPF, or southern pine, let's say you've got a hardwood or some sort of lesser used species that you're using in a floor joist application. This would allow you to calculate the spans for those non-standard species. So we're going to check to see if the FB prime value that you would calculate meets or exceeds the tabulated bending value in that row. And if it's lower, then if that FB prime value is lower than the tabulated value, then that's what controls, and you're just going to move up in the table to get to the correct F sub B value. So let me jump back up to the table here just to show you that. We had a 1.6 E and a required 1200 bending capacity. If you pick a species and grade that has a bending value less than 1200, then bending is what controls. You'd have to move up here, say, to the 1100 row, and you see then, okay, then that span is going to be limited to 17'3". So that's the way the table works. Again, gives you some flexibility to design for other species and grades. And what we do here then in the rest of the example is just solve for that for typical deflection and bending calcs so that those show up in the table. So again, pretty straightforward there. And this carries forward into the ceiling joist and the rafter tables as well, so we won't work through examples like that when we get to some of those tables. Next one we'll look at is table 2.7c. This is for calculating floor joist bearing stresses. This is based on a bearing area T times B. T is the joist thickness, B is the bearing length. So those are all defined up front in the wood frame construction manual, but they weren't defined here, so I thought I'd throw that in so you know what we're looking at. Let's look at a 10 pound per square foot floor dead load, a 40 pound per square foot floor live load, and we're going to calculate the induced compression perpendicular to grain stress on these floor joists. So for the one we're looking at a 1.5 inch by 1.5 inch bearing area. They're spaced at 16 inches on center. The joist span is 16 feet, and that ends up giving us a required or induced FC perp value of 237 pounds per square inch. So then you could choose from a selection table, NDS supplement or something like that, a species or grade that meets or exceeds that 237 pounds per square inch. So these are intended for single span applications. If you have a continuous span application, then the tabulated bearing stress can be multiplied by 2.5. So we're going to show you how to get that value here in the commentary. So let's jump there now to the commentary. Table 2.7c has a page 31 in the top right if you're following along in your handout. Again, a very, very straightforward calculation here for us. 16-foot span. We've got our 40 and 10 loading condition. Our spacing gives us 66.7 pounds per linear foot. We've got that bearing area of 1.5 inches by 1.5 inches. So we divide that out and come up with 237 pounds per square inch. So now if we have a continuous span versus a single span, that's going to be 1.25 WL over A versus WL over 2A. So that ratio then gives us the 2.5 factor that we would need to calculate the bearing. So you could just take a tabulated bearing value for a continuous span, multiply by 2.5 for continuous span applications. Again, pretty straightforward, easy, convenient tool for lots of different applications there. Jump into table 2.8a. Now we've got floor framing capacity requirements for that same 30 pound per square foot live load. Again, an L over D of 360, a dead load of 10 pounds per square foot, and this is going to allow us to size our I-joists. So we're going to jump down here to a 24-inch on center, and what's this, a 16-foot maximum span. That gives us an EI of 165. What are the units there? The apparent rigidity EI inch squared pounds, 2560 foot-pounds for the moment, and then 640 pounds for a reaction or shear value there. So how do we come up? Well, we'll see how to come up with that in a second. Look at the footnotes then to tables 2.8 A and B. Footnote 2, for continuous span applications, we're going to multiply those tabulated apparent rigidity requirements by 0.75. Footnote 4, shear capacity requirements for continuous span multiplied by 1.25. We already talked about calculating the bearing capacity requirements. That's the same for solid sawn as it is for I-joist. So we typically aren't going to repeat when we have a footnote that's already been talked about to just keep us moving through. So now we jump again to the commentary for table 2.8A and B for the I-joist that we looked at. 16-foot span, 24-inch on center, spacing, 30 pound per square foot live load. So these are the bedrooms upstairs. We've got our dead load of 10 pounds per square foot. So we calculate our PLFs of 20, 60, and a total of 80 for this particular application. We'll calculate an EI for that, an EI apparent, based on the L over 360 limits that we talked about. You could incorporate a different deflection limit here of 480, I think, is tabulated. You could input 720 here, come up with your own EI requirements, but this is the one that's tabulated. Then we calculate our moment, WL squared over 8, based on those same loads to come up with the 2560. And then our shear or reaction of 640 pounds based on WL over 2. So footnote 2 deals with that continuous span ratio. So when we get to a continuous span, it's WL to the 4th over 109 instead of 5 WL to the 4th over 384. So we look at that ratio here to come up with, it actually tabulates to 0.71. So we're going to just conservatively use a value of 0.75 in the footnote there. Footnote 4 then was that interior support shear requirement, and that's half of the bearing requirements that are given in footnote 3, so that's a 1.25. Okay. So that gets us just about halfway through, and I'm going to ask Marcy if she would to come back for our next poll question.
Absolutely.
And then we'll take some time for some question and answer. So if you have some questions, put those into the question box there, and Lori will come on here in a second. We'll do a little Q&A here halfway through.
Alrighty, so while we're doing that, WFCM tabulated spans assume simply supported single span floor joists. Is that true or false? So, and this seems to be a little bit harder since it's not a, cut and dried answer for y'all. So, got about 70% have voted. I'll give you about 10 more seconds. All right, it seems like the voting is kind of stopped. I'm going to go ahead and close. And we have 82% say true, 18% say false. And Buddy, what is the actual answer?
Okay, so the correct answer is true, and that is a little bit of a tricky question. The key word there that I've highlighted on the screen is the word tabulated. So the tabulated spans assume a simple support condition. Then we have all the factors in the footnotes that allow for continuous span applications. So let's bring Lori on and see if there's some questions that we can answer. I know 2 hours is kind of a long time, so if you need to take a break while we're doing some Q&A, we'll probably do that for a couple minutes here and then jump back into the webinar. Lori, what do we got?
Hey, Buddy. So the first question that we had come in was on the exam, that table you were just looking at. It was table 2.8 A and B. And there were some questions about the bearing area calculation and where that one, I believe you said it was 1.5 inches by 1.5 inches was the bearing area on this guy.
Okay.
Some questions about where that came from.
Oh, okay. So we tabulate various different bearing areas. And sorry for scrolling on the screen here. Let me just jump up so you can see. The table 2.7C, we tabulate both 1.5 by 1.5 and 1.5 by 3.5. The example that we solved was just for the 1.5 by 1.5. But that would be, for example, say a joist framing over top of a girder truss or rafter framing over top of a single ply application. So we're just we're allowing for those smaller bearings if they're, if you can calculate them. That is the minimum bearing, I believe, specified in the code, but you could specify, or you could calculate those minimum bearings of 1.5 inches if you had a smaller bearing area. Another one would be like a joist hanger, for example, might have that smaller bearing area. So that would allow you to determine whether you've got enough compression perp to handle that in a joist hanger. So that would have been the easier answer. Sorry.
Okay. Oh, wow, we got a lot of questions coming in. Let's see. Okay. Is there any restriction? We have a maximum restriction on the roof pitch, but is there a minimum required roof pitch when we talk about our rafters?
Okay, another good question. So you can let me just make sure I answer that correctly. I'm pretty sure we go from 0 to 12 and 12, and that's going to be in that table 2, which leads off the chapter 2. So let me jump there before I say something wrong. Yeah, flat. So table 2 for rafters allows you to go flat up to 12 and 12. Now, the provisions for where you can use a ridge board, however, kick in at 3 and 12. And so we talked a little bit earlier about that. So below 3 and 12, you have to use a ridge beam. A ridge board then could be used above 3 and 12. So that's a good question.
All right. Keeping in that line of thoughts, we had some folks that were questioning exactly how does a thrust load develop?
Okay, so for again a ridge board application, we've got snow loads on the roof, and let me see if I can get back up here to a picture. So, pardon the scrolling, but we'll jump back up here, and there it is. So maybe that'll give us a good one. So we've got these dead and live loads on the roof, and that, let's say that what's defined there as the ridge is a ridge board. If this is a ridge beam, then we don't have those thrust loads. If this is a ridge board, however, we've got those loads pushing down vertically on that triangular shape there. And as you can imagine, if there's nothing there, let's pretend for a second that there's no ceiling joist, no rafter tie, and you push down on top of that triangular structure, it's going to push the walls out. That's really what we're doing, is resisting that outward thrust, keeping it from pushing those walls out with a ceiling joist or a rafter tie. So good question. Glad we could clarify that a little bit.
All right, great. Let's see. Got time for probably one more and we'll get rolling again.
Okay.
All right. I think you're going to talk about this one in one of the tables that's coming up, balanced versus unbalanced snow loads.
Yes.
That's an upcoming one. Okay, so we'll save that question for later then.
Yep. Good call.
Okay.
I'll tell you what, Lori, why don't we go ahead and move on?
I think that's all. We'll get rolling again, and then we can jump back into it at the end.
Yep, if you have some that come in between now and then, just save those up and we'll address as many as we have time for. So now we're on to table 2.9b, and we'll start looking at calculating exterior wall stud compression stresses. So we've got all the loading assumptions here just below the title of the table. Our dead loads are a roof of 20 pounds per square foot, a wall of 121 pounds per linear foot, floors, dead load of 10 pounds per square foot, and then our floor live load of 40 pounds per square foot if there is a floor involved. And you can see the roof and ground snow loads across the top of the table here. So first column is the roof live load, designated RLL. Then we get to 30, 50, and 70. GSL stands for ground snow load. And then we've got our building width for each of those up to 60 feet in increments of 12. And then we're going to calculate an induced F sub C, a compression stress. And this is going to be based on a certain stud spacing, either 12, 16, and 24 inches, and a stud size varying from 2x4 to 2x8. And then you see here, we'll look at that for different configurations of roof and ceiling and floor. So as we move down through the table, then we add floors, and some of those are clear span floors, some of those are have an interior support. I want to get down here to the example that we'll look at in the commentary. So on page 83, we've got a 50-pound, we're going to be looking at a 50-pound per square foot ground snow load, a 36-foot building width, and looking at a roof, ceiling, and 2 clear span floors. We're going to look at studs at 12 inches on center, and they're 2x6s. And for that particular configuration, we calculate 338 pounds per square inch of compression stress. All right, so let's work our way down and take a look at the footnotes before we jump to the commentary. That tabulated compression stress, FC, shall be less than or equal to the allowable compression stress perpendicular to grain, that's FC perp prime, for the top and bottom plates. So we talked about earlier sizing top and bottom plates, so we're going to look at FC perp for top and bottom plates, and less than or equal to allowable compression stress parallel to grain for the studs, which is FC parallel prime. So those are all calculated by the designer, but the stresses are easily pulled from these tables here. Now, one more thing I want to highlight for you, and that is some of the, looking back up here at our 338 tabulated value, some of these have an asterisk next to them. So over here for a lower ground snow load, I think this is the 30 pound per square foot ground snow load case. In that particular case, the load combination dead plus floor live is what controls. Excuse me. So in that case, you are permitted to reduce your unit loads for combinations that include roof live load and ground snow load. So that's just a note there to let you know what controls so that you can accommodate accordingly for roof live and ground snow loads for those other load combinations. So then jumping to the commentary for table 2.9b, again this is a pretty straightforward analysis here, but we had that roof ceiling and two clear span floors, a 36-foot building width, 2 by 6s at 12 inches on center, and a 50 pound per square foot ground snow load. So to calculate the compression load over here in the second column, we need the total load on the stud, and the first thing you see here is that we're taking a header load from table 211. You're like, well, what's going on there? Well, this kind of simplifies our commentary and our calculation approach and shows you where these loads are coming from. So just hold this thought here for table 211. I'll show you where this value of 2665 comes from here in a second. But that's based on the gravity loads above. And then we're going to add a wall to that, and that wall dead load is 11 pounds per square foot, ends up being 121 pounds per linear foot, and so that gives us a total of almost 2,800 pounds per linear foot of total load, and then we figure out our point load there, which ends up, since we're at 12 inches on center, ends up being the same, which is almost 2,800 pounds. So then to calculate the compression stress, we're just going to take that point load, divide by the bearing area of that stud. I believe it was a 2 by 6 if I'm not mistaken. Has a bearing area of 8.25 square inches to give us our compression stress of 338 pounds per square inch. So again, we'll get to this header load here in a second from the rest of those loads above, and you'll see where that comes from. We also tabulate for interior load-bearing walls. So jump into table 2.9c, interior load-bearing walls. Not too different here, so we won't spend a lot of time, but for this particular configuration we ended up with 248 pounds per square inch. These don't carry any roof load, so take a look at the red note down there in the bottom right of the table. The members shown in this table don't carry any roof load. These are just interior floor loads being carried here. So again, a couple of different tables, same type of calculation approach here to come up with that value of 248 pounds per square inch. So we won't belabor going back through that analysis, so it'll give us some time to get into some of the others. And that takes us to table 2.11, which is one of the more useful tables in Chapter 2. And this allows you to calculate the load-bearing wall loads from snow or live. And so, as I mentioned earlier, I'd show you where one of those loads comes from. So let's jump down here to the bottom. Let me see if there's anything I got to show you at the top. Wall studs, headers, and girders. So again, a pretty utilitarian table here for studs, headers, and girders. You see all the dead and live load assumptions here. You see the nomenclature. RLL is roof live load, GSL ground snow load. We see our roof span in increments of 12 feet, and we're going to calculate unit header loads for different building configurations. So I'm going to come down here to the bottom left of your page, and based on a 30 pound per square foot ground snow load and a roof span of 36 feet, we calculate a value of 2442 pounds per linear foot. And you asked me, or I mentioned a second ago, I'd tell you where that header load for the wall system came from. It's right next to the one we're calculating here. It's circled in, or it's got that square red box around it. So that value is what's used in the previous table to calculate the stud wall compression stress. But for the one we're going to calculate here in the commentary, we're going to be calculating 30 pound per square foot ground snow load. And again, because of the fact that some of we've checked multiple load combinations, we'll show you those multiple load combinations. This one has an asterisk next to it, and that indicates that dead plus floor live controls, and that you could reduce your unit loads if you've got roof live and ground snow load combinations. So let's jump to the commentary, to table 211, and again that's for load-bearing wall loads. So here then is a table that's going to be pretty instructive, I think, for table 211. We are following ASCE 7 load combinations. But what's unique to wood is the fact that we also apply a load duration factor to our strength properties. So when designing structural wood members, it's necessary to consider the load duration factor when looking at various load combinations. So the bottom line is you cannot just take a load combination, come up with a maximum load, and say that's the one I will use, because as you see here in this table, the governing load duration factor gets applied when designing those structural wood members. And because wood has that unique capability of carrying a higher load over a shorter duration, what you may find is that for a roof live load combination, for example, which can be increased by a factor of 1.25, that load duration factor actually offsets a larger load combination. So I know that may not be it might be a little bit hard to digest, but that's the point of this particular slide and this particular table here, is that we're looking at various load combinations, and the note here below the table indicates as a result of the 0.75 factor in combinations 4 and 5 and this load duration factor, some of these will be controlled by floor live load rather than the roof live or snow load combinations. So that's all accounted for in the tables that are being calculated, but you need to know that as a designer going in as well. So for the load combination that we're looking at, dead plus live, dead plus snow, and then the dead plus 3/4 live and 3/4 snow, we're going to look at calculating the value that we had in the table. So we come up with a total load of 1,000 pounds per linear foot, and we're going to again look at balanced and unbalanced snow load. So hopefully we'll answer a question that someone had earlier about balanced versus unbalanced snow loads. And for our balanced snow load, we take the ground snow load conversion we did earlier. We come up with 23.1 pounds per square foot, and that gives us on the right-hand side a load of 462 pounds per linear foot. Now, because our building width is less than 40 feet, for our unbalanced snow load case, we use 30 pounds per square foot. And then we get to the top of the next page. So let's take a look at this paragraph, and I want to point you then to the link at the bottom of the page in just a second, because we're not going to have time to go through this in a lot of detail. But this paragraph here is what you can study. You can download a paper off of our website that gives you a lot more background, but this is how you interpret ASCE 710 with regard to balanced and unbalanced snow loads, and up to 40 feet, and or up to 40 feet we're going to use the ground snow load, but then there's a more complex analysis above 40 feet. So again, we could probably do a webinar alone on just this topic, and maybe we will someday, but for now you'll just have to trust that we've done this analysis, we've done it correctly, and that's what leads us to the unbalanced case governing. But we do check both in the tables in the analysis, so it's not just a black box. We've checked balanced and unbalanced snow loads. The bottom of the page here in red, I don't think I got that in your handout. Apologize for that, but Brian will chat that out for you in the chat box. If you want to link to that and download that paper, it gives you more of the background for what we've covered here in the commentary. So the rest of the analysis there in the right-hand column is showing how we come up with then the loads that show up in the table, the 42 pounds per linear foot that shows up in table 211. So this final note here then is what we talked about earlier with respect to the controlling load duration factor. And so if you have a load duration factor, or if you have a load in that table with an asterisk next to it, then that is controlled by dead plus floor live, and you could therefore use a C sub D of 1 when designing for that header application versus a 1.25 or a 1.15. All right. So that takes us then to ceiling joist spans. Table 212A1 is for live load of 10 and a L over 240 deflection ratio. That L over 240 is for flexible finishes like gypsum board. By the way, new to the, I think, 2012 and 2015 code are these higher deflection limits defined in the IRC for flexible finishes. Like gypsum, it's L over 240. For brittle finishes, it's L over 360, and that's why we tabulate L over 240 and L over 360 tables. For the example here, we've used the L over 240 table. Again, using a standard E value 1.4, we're going to calculate a required bending value for that. We go to the commentary. Again, similar to what we looked at before, we can solve for those values in the table for deflection and bending check. Reference here back to commentary 2.7a and b for a similar example that we looked at just a second ago. Then we got the capacity requirement tables, again allowing you to use other products other than solid sawn, and here we're calculating an EI, M, and V or bearing value. So we've worked through that once for the floor applications. We won't spend a lot of time on that here, so we'll keep on moving, get to some other things in the book. So this is the commentary to that table that we just looked at for calculating the EI apparent, moment, and reaction or shear at the ends. And again, back to a similar example in 2.8a and b. So I'll ask Marcy, if she will, to come back and lead us in our next poll question.
Absolutely. So, WFCM tables can be used to design for ground snow loads up to 20 pounds per square foot, 50 pounds per square foot, 70 pounds per square foot, or 90 pounds per square foot. All right, we're going to have just a few more seconds. All right, I'm going to go ahead and close. And then sharing. All right, so 71% said 70 pounds per square foot, 18%, 50%, or 50 pounds per square foot, and then just a few said 90 or 20%. So hopefully it's either C or B, 70 pounds per square foot or 50%, 50 pounds per square foot.
Yep. And the answer is C, which is 70 pounds per square foot.
I am so sorry, buddy. I've lost my screen here, so give me a minute to...
Okay. Not a problem, but the correct answer is 70 pounds per square foot. So as soon as... I wonder if I were to hide it, what that would do. Well, tell me if you can't recover it, and I will do it.
Okay, here we go.
All right.
There we go.
So if you're seeing my screen again here, hopefully in a second, there it is. So the answer is 70 pounds per square foot. So we've had requests to go higher for some of you folks up on our northern borders, but again, that gives us some pretty significant load path issues that we have to deal with. So maybe some point in the future as we continue to evolve the wood frame construction manual, but for now we're limited to 70. So let's then look at rafter spans. Again, because we've done similar calculations already. The one nuance here in Table 214A is that we actually tabulate a fairly standard bending value here in the first column under the 10 pound per square foot column, and then calculate for other dead loads and E values depending on the deflection limit. You can see again this issue of flexible finish at L over 240 and brittle finish for like plaster and stucco for L over 360. So if you had a finished attic, for example, and you're trying to keep your deflection limits so that you're not cracking the gypsum or the plaster in the rafter in the ceiling, then you'd stiffen up those rafters with this approach. So we'll get to footnotes to this table, 214A, and here again coming back to our discussion about increasing loads when we take the ceiling joist and raise it up and now it's a rafter tie. That rafter tie not only increases the connection requirements, but it's also going to put a twisting moment, an additional moment. If you're looking at the figure here just to the left of the table, where that arrow with the T comes off of the rafter, if that's where our rafter tie is located, it's going to create an additional moment on that rafter because of that load. And so these adjustment factors to the right in the table, and in this case for 1/2 the adjustment factor is 0.58. So what that's saying is that we're going to take the span that you calculate and we're going to knock it down by a little bit more than 40% because of that additional moment that's induced into the rafter there. So you can, again, you see the significance of this for ceiling or for applications where you don't have a ridge beam. Instead you have a ridge board and you're using those rafter ties to resist that outward thrust. It makes a dramatic impact on sizing rafters and connections. And again, the note there about once you go above 1/3 looking at deflection issues in the rafter because of that additional moment, the additional loads, you're going to have additional deflections there that you need to account for as well. Footnote 2, you may or may not be aware of a provision in ASCE 7. It's the sloped roof adjustment factor. And so we'll call that out here, and for this example we've got a 6 and 12 roof pitch, and that factor is 1.04, but you see we tabulate those for various roof pitches and dead loads, and so we'll look at the commentary to see where those come from as well. So here we are in the commentary. I want to talk a little bit about rafters and what's a little unique for those versus a floor joist or a ceiling joist. It is based on a simple bending calculation, assuming that the rafter is simply supported at each end, and the span is assumed to be equal to the horizontal projection of the rafter. Now that is a simplifying assumption. We realize that. We know that's the simplifying assumption that's in the building codes. A more sophisticated approach, and you can see the bullet list here, would take into account compression stresses in a rafter when a ridge board replaces a ridge beam, additional bending and compression loads provided by compression capacity, provided by the roof sheathing that we don't account for, increased length of the sloped rafter relative to the horizontal projection, reduced loads using a sloped rafter length relative to that horizontal projection. So all of those are sort of trade-offs that we know exist, and we know we can live with to come up with the simplifying assumption of this horizontal projection approach. So you can certainly, as a designer, take a more rigorous look and account for some of these other things, but this has been accepted practice, and within the limits, again, you know, the span limits that we have in the wood frame construction manual and the load limits that we have feel like are realistic assumptions, and our ANSI committee has agreed in that regard as well. So I wanted to make sure I talk about that. The rest of the calculations there are very straightforward. I do want to point you though to footnote 1 and the background for footnote 1, and that has to do with the rafter ties. And this then provides the background calculations for determining that increased moment on the rafter because of that rafter tie being located above the top plate. And so you see the calculations here. Again, we can't delve into them in detail, but you know they're there now, and you can take a look at those. And that's how we come up with the calculations. Now, shown here at the top of this page, that 0.58 factor that shows up counts for that additional moment because of that rafter tie application. Note here, and then what's highlighted is deflection of the wall is also a function of the thrust connector, the vertical wall, the roof load, and if you want to calculate wall deflection, we've given you those calculations here. And unfortunately, when I was going through this and trying to prepare for today, I noticed that we have a little bit of a typesetting issue. So you see the red box here. This part of the equation and part of the commentary got kicked to the bottom somehow in typesetting. So if you've got your notes there and you want to make a note of this, that sentence and deflection equation should bump up here to this section right above footnote 2. That's where that belongs, and we'll get that fixed in a future edition. I have to note, however, that that was also in the 2012 edition, so this has gone unnoticed now for 2 editions of the standard. So I apologize for that, but we'll get that fixed. You can fix it in your version and be in the know. So footnote 2 then deals with that ASCE 7 provision. Section 4.8.2 of ASCE 7 provides for that roof live load reduction. So we calculate that, tabulate that, and so the one that we came up with comes from just basically calculating a new rafter span based on that reduced live load, and then doing a ratio to what the tabulated span is without that live load reduction. So those also are built into the tables as well. So keep moving here. That was the live load table, rafter live load table. We also differentiate the rafter tables for ground snow loads, again up to 70 pounds per square foot. And again, in the interest of time, we won't spend a lot of time here because we've already dealt with all of these issues, so I'll keep moving through here. The commentary to that table shows how we resolve that. Again, accounting for balanced and unbalanced snow loads. Roof framing capacity tables, 215A, allow us to calculate for I-joists and other engineered wood products. So yes, you can use those in rafter applications as well. I believe we've covered all the background for all the footnotes in this table as well, so we won't repeat that. And then the commentary for table 215A shows up next. So moving right through the provisions here. And we actually may have duplicated a table there, so I apologize if we did that. Yeah, I'm not seeing anything different there, so I'm going to ask Marcy, if she will, to come back and lead us in our next poll question.
Sure, and I think this might be our last one, but let's see. So let's turn it on. WFCM rafter spans are based on the actual member length. Is that true or false? All right. So I've got about 65% of you have voted, so a few more. All right. It tops out that about 75% of you like to vote, so there's a few that don't. So I'm going to go ahead and close and then share. So 85% say false and 15% say true. So, Buddy, what is it?
So the correct answer is false. And hoping you all are still hearing me. It sounded like something got cut off there. Lori, can you or Marcy just make sure that my audio is still working? I heard something kind of
You sound clear to me.
Okay,
yeah, I
great.
can hear you.
Good. Okay.
And people
Just
say
want to
yep.
make sure. All right, good. So the answer is false, and the key there is that we talked about horizontal projection of spans. We went through that bullet list of how we could look at the actual member length, but we don't. We use a horizontal projection to calculate rafter spans in the wood frame construction manual. So we'll keep on going and move then into the ridge beam table. So this is a pretty straightforward table here, but we will take a little bit of time to talk about some of the other things you need to consider if we're going to use a ridge beam. So for this particular example in table 216, we're looking at a roof dead load of 10 pounds per square foot, a ground snow load of 50, and a roof span of 36 feet. Gives us a unit ridge beam load of 873 pounds per linear foot. So we jump to the commentary, and again, really straightforward here. It's just a tributary span equal to half of the roof span to calculate that. And so we've got a snow load here where we're going to calculate a roof snow load from a ground snow load of 50 pounds per square foot to give us 38.5 pounds per square foot. And then we'll add our dead load to that to give us 48.5, and then we'll calculate our total load, and based on the roof span of 36 feet, then come up with 873 pounds per linear foot. But let's talk about a couple of things, and they have to do with load path. So if you're going to go with a ridge beam, that means that your non-load-bearing walls have to have a way to take the loads at the ends of each of those ridge beams down into the foundation. So let's assume, for example, that you've got a two-story building, and a typical gable end was a 7/12 pitch and a ridge beam running across that. You could span a ridge beam, pretty good distance with a glue-lam or built-up solid sawn member. But that means you've got some pretty high loads at the ends of that ridge beam as well. And so those loads then have to be transferred through probably some sort of a stud pack or a 4x4 or several 4x4s under that beam, and that would go into your gable end, the triangular gable end, your second floor, and your first floor down into the foundation. So no window and door openings could interrupt that. And then we'd have to look at the other direction, which is uplift. And I know we said we talked about that last week, but we didn't really talk a lot about ridge beams in last month's webinar. So you'll also have wind uplift on that ridge beam and from the roof. So you're going to have to strap that ridge beam to the or connect it to the stud pack or the 4x4s or whatever you've connected to carry that gravity load. Now that's acting to tie in the ridge beam so it's not lifted up off the structure, and that needs to go all the way through. So those are additional considerations for ridge beams that you have to account for in the design process. Again, we don't provide a lot of solutions for that because those are so unique and so many variables involved. But as a design professional, those are things you certainly have to consider. All right, so we'll wrap up here with the hip and valley beam capacity table, and then it looks like we'll have plenty of time for Q&A. If Lori, if you want to start getting some of those organized after we finish up the hip and valley table. So we've got, again, deflection limits here, similar to what we've looked at before. We've got different dead load cases. In this case, we're going to look at a 20 pound per square foot dead load. Forgot to highlight this. We're going to look at a L over 180 deflection limit, so no ceiling attached to this one. We're going to come down and look at a 30 pound per square foot ground snow load and a 12 by 12 foot area, which again, based on a horizontal projection, is going to give us a 17 foot horizontal span for that hip or valley rafter. And so based on that, we'll calculate the apparent rigidity, the EI, the required moment and bearing conditions for that hip or valley rafter. So I believe footnote 1 here is the one I want to make sure I point out to you. The apparent rigidity capacities need to include the effects of bending and shear deflection. So the apparent rigidity capacities have been adjusted for solid sawn to account for those effects. But if you're going to use a structural composite lumber, you need to make sure that you contact the manufacturer for those capacities if you're going to use structural composite lumber for these applications. And we're live load deflection only, which is pretty typical for these applications. So, commentary to Table 217. Given that 12 by 12 hip or valley area and the load conditions that we talked about, the length of that rafter is 17 feet. So we're, up here under background, let's just note that triangular loading is imposed for the members framing into the hip and valley. So we'll drop down here a little bit and we'll calculate the length of each of the jack rafters based on their location. You see the locations here and the loads imposed, P1 through P5. Kind of looking at the top of the page here, I want to define some terms. The A is the location along the hip or valley, J is the jack length, L is the live load, TL is the total load. And then we're going to use superposition. I was joking during practice, I haven't used superposition since college, but we're just going to calculate each of these and then sum them up to come up with our apparent rigidity, EI. And so the table here at the bottom of the page just gives us a real good sense of the geometry, the lengths, the live loads, and the total loads for each of those jack rafters. So jump into the next page then, 51. We're gonna do an EI total based on 2 times the sum of each of those EIs that we calculate, because we're going to account for loads from jack rafters on each side. So we're going to calculate EI at location 1, 2, 3, 4, 5. We come up with a value of 79 million multiplied by 2 gives us what is that, 158 million inch squared pounds for our EI apparent for that particular hip and valley rafter. So similar superposition calculations used to calculate the reaction at the top. We'll calculate R1 through R5, sum those up to come up with a reaction of 1,580 pounds, and then calculate our moment, our maximum moment, where shear is equal to 0. Okay, and so it says somewhere that occurs at jack rafter number 3, because that's where our 0 shear location is, and so we'll sum moments to come up with a moment of 6583 foot-pounds. So some of you may be wondering how does this work really, because we've got this hip roof and there's really not there's not a ridge beam here, so what's holding up the upper end of that jack that hip or valley rafter? And it's really the triangulation of the rafters that are running along the ridge and the ceiling joist or rafter ties. So it's really important at this particular location, because it's that location is picking up a lot of load there. We're not accounting for folded plate action, a lot of things that, well, actually, I guess we are accounting for it, we're just not calculating based on that. But there's these hip systems, I won't say they work magically, but they work in a way that we can't necessarily calculate all the fine details out. And we've had actually some folks doing some research in this area. This will eventually probably lead to a PhD thesis at some point, looking at these loads and how they're distributed in a hip system. But again, back to the comfort level that you can have knowing that we've got span limits on the wood frame construction manual, load limits on the wood frame construction manual. We've had a consensus group of experts over the past 15 years looking at this, and we've got a history of structures working with this particular approach as well. And so with the limits we've set in the manual, I just have to say that this it works. This is a calculation approach that is here for you as a design professional. It is one method of doing the calculations. It's not the only method, and so as a design professional, if you want to use a more rigorous approach, you have options obviously to do that and work with your code official on those calculations. But I'm going to stop there. Sure, we'll get a lot of questions about that. I've probably exhausted everything I know about that particular subject, so I'm not sure I'm going to be able to answer much more than that, but I'll bring Lori back and see if we've got about 10 minutes worth of questions that we can cover.
We have a lot of questions. I don't know if we'll be able to get through all of them, but the first one is, are we allowed to interpolate on the tables if we are in between two columns, for example?
Great question. And there is a provision in the wood frame construction manual that specifically addresses that. Let me see if it might be up in chapter 1, so I'm going to flip through here real quick and see if it mentions that. I know it does in chapter 3, but I'm pretty confident that the answer is yes. I'm just not finding it here at my fingertips. It's probably buried in one of these provisions at the beginning of chapter 2. So I'm going to say yes because I know I've interpolated some of these tables. As a designer, you're going to want to use judgment doing that. But I think the way that it was written, at least in chapter 3, is that interpolation is permitted unless stated otherwise. So, all right, there it is.
We got some 2.14. Thanks, guys.
Yeah, I just as you said it, I just found it. So thank you. Yes. Tabulated values shall be permitted to be interpolated unless otherwise noted in the applicable footnotes. Also want to mention to folks before you ask your next question, Lori, because I know Marcy's probably saying this in her head, you folks want to stick around to make sure you get all of your contact out, all your minutes, your 90% or whatever that percentage is that Marcy mentioned. So don't drop off because this Q&A still counts toward your 2-hour threshold as well. So what's our next question, Lori?
Our next question was on our ceiling joist tables. Do we assume it was for our uninhabited attics, did we assume our ceiling joists in those situations to be braced or unbraced?
Boy, that's a really good question. And I'm pretty confident that our assumption is braced for all of our joist applications. So that would apply. That would mean that we'd have gypsum on the underside of those joists, which would serve as bracing. And I know you're saying, well, that's not on the compression edge of the member, but I have to look somewhere where we say if you're least sheathed, and it might be in the NDS Appendix A that I think, Laura, you and I might have talked about this the other day, where if you're adequately sheathed on at least one side, the depth shall be permitted to be taken as the least dimension. So yeah, gypsum. We're going to assume gypsum, and we're going to assume that braces it, even if it's on the opposite side of the compression edge.
Okay, great. There were some additional questions. I think table 214, any of those probably would be a good one to flip to, and I just wanted to clarify for folks.
Okay.
We have in the first column, or in the first couple of columns, we provide a small f sub b.
Ah, okay.
And we want to clarify how that would compare to our capital F prime B, which would be in the NDS supplement, our unadjusted value, and our adjusted values that we calculate.
Yeah, great question. Good one for us to be able to clarify. So here in 214A, for example, it's showing up on your screen, and I can actually make this one a little bit bigger since we're talking about this factor up here at the top. We've got a value called f, lowercase f sub b, and that's the bending stress. And so bending stress is, let me get to the right place here so I make sure that I say this right, but this is it's kind of a mix of allowable or actual bending stress and allowable. So we're gonna tabulate what we would call an actual bending stress, little f sub b, even though it looks like it's just a number like you'd see in the NDS supplement. But we're going to compare that little f sub b against a capital F sub b, and I want to jump to the commentary and see if we define those terms a little bit better in the commentary. So we're going to perform span calculations for a given set of E and F sub B properties. So we drop down here, and here's our equation where we're calculating F sub B. That actual F sub B would need to be greater than, and this WL squared over 8 represents the moment divided by the section modulus. And so when we sort of calculate that or tabulate that, then what you would do for your design process is you open up your NDS and NDS supplement and you calculate an allowable F sub B. So you pull properties out of the NDS supplement for Southern Pine number 2, 2x6 has a bending capacity of 1200 psi, for example. And you can adjust that for load duration and repetitive member and other adjustments to come up with an allowable an allowable F sub B to compare to that actual. So it's kind of probably not a great explanation, but the designer has to calculate that allowable F sub B from the NDS and the NDF supplement to compare against this tabulated F sub B in one of these tables, and same with the E value to make sure that you've got an E that meets or exceeds this tabulated value.
All right, cool. Can you talk a little bit about we talked about the adjustment of our snow loads from a ground to a roof load. We also had a lot of questions, people asking any live load reduction that happens on our roof rafters. So this would be a good table to talk about that.
Yeah, so I talked about this, and this is in table 214A. And footnote 2 has the live load adjustment factors. So this is from ASCE 710. I can't remember the section number. It's in the commentary. But this table right here with footnote 2 gives those live load adjustment factors. And what these, since they're greater than 1, that allows you to increase your span over the tabulated span. So you're increasing your span because of that live load reduction. So I'll jump down here, and footnote 2 is ASCE 7-10 section 4.8.2. So that was a question that we hopefully addressed a couple of times.
Okay.
Last one.
All right, one more. For our hip and valley calculations, do we have anything that would allow folks, if they have mismatched roof slopes meeting up at their hip or valley, is that allowed in the WFCM?
No. These are symmetrical. And so we really don't have anything there to offer you other than this analysis approach that we show here kind of gives you an idea of how you can approach it. And so then you could, using this approach, come in with different EIs from different sides. So instead of multiplying by 2 here, you just calculate it coming in from different sides. And, but these assume a symmetrical hip and valley. Sorry about that. Well, thank you all. We're at the top of the hour, and so I'm going to ask Marcy to come back and close us out for today. And appreciate you tuning in and all the good questions that you had for us today, and hope you come back next month for some column and beam design.